In this video, we're finally going to come to the technical highlight of bottom-up parsing. So after all the definitions of the previous videos, now we're actually going to be able to give the algorithm for recognizing viable prefixes. So let's dive straight into the algorithm. The first step really is just a very technical point, and it's not that important, but we're going to do it anyway because it makes things simpler, is to add a dummy production. S prime goes to S to our grammar of interest G. So just to set the stage here, we're trying to compute the viable prefixes of G. We're trying to come up with an algorithm for recognizing the viable prefixes of G. If S is the start symbol, we're just going to make up a new start symbol, S prime. So S prime will be the new start symbol of the augmented grammar. And there's just one production for S prime goes to S. All right, so this just allows us to know exactly where our start symbol is used. In particular, our new start symbol S prime is only used in one place on the left-hand side of this one production. And that just makes things a little bit simpler. Now, recall what we are trying to do. We claim that the set of viable prefixes for a given grammar is regular. And so what we're going to do is we're going to construct a non-deterministic finite automaton that recognizes the viable prefixes. Okay? And the states of this NFA are going to be the items of the grammar. Now, the input to the NFA is the stack. So the NFA reads the stack, okay? And then so let's just indicate this. So the NFA is going to take the stack as an argument, and it's either going to say, yes, that's a viable prefix, or no. And it's going to read the stack from bottom to top. So it's going to start at the bottom of the stack and read towards the top of the stack. And our goal here is to write a non-deterministic finite automaton that recognizes the valid stacks of the parser. So that's how we'll know that our parser hasn't encountered any parse errors, because this automaton that we're going to construct will always output either yes, this stack is okay, meaning it could wind up parsing the input, or no, what we've got on the stack now doesn't resemble any valid stack for any possible parse of any input string for this grammar. Okay, so let's think about what we need the moves of this machine to be. So let's say that we're in the state E arrow alpha dot x beta. Now what does that say? So that says that so far we've seen alpha on the stack. Okay, so remember, the machine is reading the stack from bottom to top. This records the fact that the machine has already seen alpha on the stack. So what would be an okay thing to see next on the stack? Well, if this is a valid stack, if having alpha on the stack at this point is valid, well then certainly it would be okay if the next thing on the stack was an x. So we have a transition that if we're in this state where we are working on this production and we've seen alpha on the stack, if the next thing is an x on input x, then we can go to this state where now we record the fact that we've seen alpha x on the stack and we're waiting to see the remaining portion beta of that production. Okay, so this is one kind of move that the non-deterministic finite automaton can make. And again, we add this kind of a move for every item. So for every item in the grammar, if the dot is not all the way at the right end, then there will be a move like this where the dot moves over for whatever symbol happens to come to the right of the dot. The other class of transitions are the following, and these are the more interesting ones. So let's say that we're in this configuration here, where again we've seen alpha, and then the next thing on the stack is x. And here, x is a non-terminal. And I should have said that in the previous case, x was either a terminal or a non-terminal. So this x here is any grammar symbol, not just a non-terminal. But this number 4 here, the moves here at part 4, are specifically for non-terminals. Okay, so anyway, if x is not on the stack, okay, let's assume that we've seen alpha, and then the next thing on the stack is not x. Well, is it possible that there could be a valid configuration of the parser where we saw alpha, but then x didn't appear next? And the answer is yes, because, as we said before, the stack is a sequence of partial right-hand sides. So it could be that all that's on the stack right now for this production is alpha, and that the next thing on the stack is eventually going to reduce to x. Might not be x itself, it might be something that will eventually reduce to x. Well, what does that mean? Well, that means that whatever is there on the stack has to be derived from x. It has to be something that can be generated by using a sequence of x productions, because eventually it's going to reduce to x. So for every item that looks like this, and every production for x now, we're going to add the following move. We're going to say that if there's no x on the stack, well then we can make an epsilon move. We can just shift to a state where we try to recognize the right-hand side of something derived from x. And these are the only two kinds of moves. Either the either the grammar symbols we're looking for are there on the stack, and we extend the prefix of a right-hand side. So this rule here extends a prefix, says yes, we see more of that production on the stack, or it tries to guess or tries to discover where the ends of the prefixes are. So if alpha is as much of the production that is on the stack currently, well then this must be, this x here must, this point here must mark the start of another right-hand side in our stack of right-hand sides, and we would expect to see something derived from some production for x. Two more rules. Every state in this automaton is going to be an accepting state. That means that if the automaton manages to successfully consume the entire stack, then the stack is viable. And just notice that not every state is going to have a transition on every possible symbol. So there will be plenty of possible stacks that are rejected simply because the automaton gets stuck. And finally, the start state of this automaton is the item s prime goes to .s. So remember, the states of the machine are the items of the grammar, and this is why we added this dummy production, is just so that we could conveniently name the start state. So now let's consider one of our grammars that we've been using a lot. So this is the grammar, and now we're going to augment it with the extra production, s prime goes to e. And let's take a look at the automaton that recognizes the viable prefixes of this grammar. And here it is. And as you can see, it's rather large. It has a lot of states and a lot of transitions. And I just want to show it to you here before we describe how we calculated it, just so you get an idea that these automata for recognizing viable prefixes for grammars are actually quite elaborate. But now let's break this down and see how it was produced. So let's begin with the start state for this machine. So we have s prime goes to .e, and remember what this says is we want to be able to reduce to the start symbol, to our new start symbol, and so we're reading the stack and we're hoping to see an e on the stack, but if we don't, then we'll be happy to see something derived from e. So what transitions can we make from this state? Well, one possibility is that we do in fact see an e on the stack, and in that case the dot simply moves over saying yes, we've read the first item on the stack, or we've read the e on the stack, and so we've seen the full right-hand side of this production. Now, that would indicate that we were probably done with parsing. This is the state that you would reach after you'd read the entire input and successfully parsed it. You would have reduced to the old start symbol and be about to reduce to the augmented, the new start symbol. But if you're not so fortunate as to see an e on the stack, then you need to hope that you'll see something derived from e. And there are a couple of possibilities there. One is that we could see something that would eventually use this production, e goes to t. And since we haven't seen any of it yet, we put the dot all the way at the left, indicating that we're hoping to see a t, which could then reduce to e, which could then reduce to s prime. Now, if we don't see a t on the stack by itself, the other possibility is that we could be working on this production, e goes to t plus e. And again, we haven't seen any of it, so the dot goes on the left-hand side. And now notice how we're crucially using the power of non-deterministic automata. So here we don't know which production is going to, which right-hand side of a production is going to appear on the stack. And in fact, notice that these productions are not even left factored. So we don't know whether it's going to be just a t there or a t plus e. But we just use the guessing power of the non-deterministic automaton. Let it choose which one to use. And remember, the non-deterministic automaton accepts if any possible choice accepts. So it can always guess correctly. So intuitively, it will be able to pick the right one. Now, of course, we can compile this down to a deterministic machine that won't have to make any guesses. But at this level, where we're writing the non-deterministic machine, it's extremely useful not to have to figure out which of these two productions to use. We can just try both and see what happens. Now let's focus on this state, e goes to dot t, what are the possibilities there? Well, one possibility is that we see a t on the stack. And then we've seen a complete right-hand side. And notice how when the dot moves all the way to the right-hand side, that is going to indicate that we're ready to do a reduce. So we'll talk about that a little bit later, but essentially that's how we're going to recognize handles. When we finally reach a state where the dot is all the way to the right-hand side, that's going to say, this could be a handle that you might want to reduce. Now, if we don't see a t on the stack, then we need to see something derived from t, and there's a couple possibilities, a few possibilities there. One possibility is that it's going to be the production t goes to int, so since we're just starting on this production again, we just put the dot all the way at the left. Another possibility is that we're working on t goes to open paren e close paren. And a third possibility is that we're working on t goes to int times t, and in each case here, notice that the dot is all the way at the left, indicating that we're just getting started. We haven't actually seen any of the right-hand side yet. Now let's shift our focus to this production. E goes to dot t plus e, this item, excuse me. One possibility is that we see an e on the see a t on the stack, okay, in which case the dot just moves over. And the other possibility is that we see something derived from t, in which case we will go to one of the states that begins a t production. And notice here that we already have all three of those items in our automaton. We're just going to states that we went to from the item e goes to dot t. So this item, e goes to dot t plus e, can also move to those three states. Now let's focus on this item here, t goes to dot open paren e close paren. Well, there's only one possible move here. So this is only a terminal. It's not a non-terminal. So there's not going to be any possibility of having something derived from open paren. We just have to see the open paren in the input. So there's only one possible transition here, which is that we see the open paren, on the stack, and the dot just moves over. Now from this state, once again, the dot is next to or just to the left of a non-terminal. So here we might either see that non-terminal on the stack, or we might see something derived from that non-terminal. Well, if we see the non-terminal on the stack, then the dot just moves over, and we get t open paren e dot close paren, indicating that we've seen both an open paren and an e on the stack, and we're still waiting to see the close paren. But we might also see something derived from e, okay? And so we have these two transitions to the two items that begin productions for e. All right, now let's focus on this state. T goes to open paren e dot close paren. Well, again, because it's a terminal that the dot is next to, there's only one possible move. We have to see that open paren if we see anything at all. And we'll wind up with the item t goes to open paren e close paren dot. And now we've recognized the entire right-hand side of that production on the stack. Let's take a look at this item. So here, because the terminal symbol, the only possibility is to read that terminal symbol on the stack. So this would be the next item. E goes to t plus dot e. Focusing on that item again, we could possibly see an e on the stack. All right, in which case we would have recognized the entire right-hand side of this production. We'd have e goes to t plus e dot. Or we could see something derived from e, in which case we'll make a transition back to one of those two states. Now, where have we got productions left to go, or items left to go? Here, we got t goes to dot int, so we would have to see an int next on the stack, and that would be the full right-hand side of that production. Down here, we still have t goes to dot int times t. So again, there's a terminal symbol here, int, and so that would be the next thing we would need to see on the stack for this production to remain viable. And once we've seen the int, we would like to see the times. So we'd wind up in this state, and now we've got the dot next to t. So again, one possibility is that we see the t on the stack, and then we've seen the full right-hand side of this production. But we might only see something derived from t. The t might not be there yet. It might be in a state where we're still waiting for the t to appear through some sequence of reductions. But then we would need to see something derived from t. In this case, we would make a transition to one of the three states that begin the productions for t. And that's the full automaton. Those are all the states and all the transitions for the automaton that recognizes the viable prefixes of this grammar.